Hey physics babies, welcome to our new lesson. This is Unit 5, Lesson 7, and today we're going to be talking about magnetic fields and magnetic force, and we'll be using the right-hand rule. Should be fun. Let's get started. Alright, so Unit 5, Lesson 7, magnetic fields and magnetic force. The first thing I actually want to show you is what your assignment looks like for today. So this will be uploaded into Google Classroom. I'll make each of you a copy for you to type in. So as you look through this, there are different sections. Some of them say assessment. Some of them say things like notes with Miss Pop or examples with Miss Pop. If it says with Miss Pop, it's optional for you to fill it in. Essentially, those are like the notes. So I will be doing these problems, I will have these examples, and I will complete them as part of the PowerPoint. But what I need from you is to make sure that anything that says assessment is answered. Okay, so there's two questions, an A and a B, right? For magnets, there's a section on electromagnets. These are examples, and then there's a section about magnetic force. So what if it says assessment? That's your job to complete. I will not be looking at the examples. Those are for you and to help you guide your notes, especially if you are looking to take them in your notebook. All right, so let's get into our lesson. Our objective is that by the end of the day today, you'll be able to use the right-hand rule to determine the direction of the magnetic field and the current through a wire and a solenoid. And we'll also use right-hand rules to calculate and determine the direction of magnetic force. So what is a magnet? A magnet attracts objects such as iron and steel. A magnetic force can be exerted when objects are not touching. So it's just like gravity and electric forces. This is actually really cool. This is an image of the magnetic fields around a magnet. All right, so magnets have poles, all right? And then the magnetic pole is the area of the magnet where the magnetic force is the strongest. Every magnet always has two poles, a north pole and a south pole. Our two north poles will repel each other. Our two south poles will repel each other, but opposite poles attract. Kind of like charge, right? Two positive charges will repel each other, but a positive charge and a negative charge attract each other. All right, so what if our magnet breaks? No matter what, that magnet is still going to have two poles. So if I took this magnet right here and we split it down the middle, we would get two new magnets and each would have a north pole and a south pole, a north pole and a south pole. Kind of crazy, right? All right, so moving into magnetic fields. Magnetic fields surround a magnet and exert a magnetic force on other objects. So our field lines, very similar to how we draw electric fields, right? From those charges. Our magnetic field lines are shown leaving the North Pole and entering the South Pole. Because this is a bar magnet, those field lines kind of swoop around from the North Pole towards the South Pole. Just as in with electric fields, the closer our field lines are together, the stronger the field. Farther apart lines mean the field is weaker, and fields will always be strongest at the poles, just like an electric field is strongest really close to the charge, okay? All right, so right now I would recommend you pause the video and complete the section of the note assessment page that's titled Magnets Assessment. So like one question with a part A and a part B. And when you're ready, I'll be here for you. All right, so magnets are really cool, but like, let's talk about some practicality behind them. And with magnets come compasses. So Earth is like a giant bar magnet, okay? The north magnetic pole of Earth is actually physically a south polar magnet, okay? And then the south magnetic pole of the Earth is physically a north pole. So that kind of doesn't make sense. Let's look at this picture, okay? So this is Earth, right? Here is North America, Dallas, we're probably somewhere like right around there. So the North Pole, our idea of north, is magnetically south. And then the South Pole of the Earth is magnetically a North Pole. So our compasses contain a very small bar magnet, and the magnet aligns itself based on the poles of Earth. A compass points north because, right, that north end of the bar magnet inside of our compass is attracted to the south pole of Earth. Does that kind of make sense, right? So a north pole in the compass wants to point up towards the south because remember, opposites attract. And then here are some pictures of, here we've got this U-shaped magnet and then a bunch of different compasses, and we can kind of see how at a north end of a magnet, the compass points away from it, right? Because opposites attract and likes repel each other. Whereas over here, we've got a south end of the magnet, all the compasses start pointing towards it because this is a north end of a magnet and it's attracted to its opposite end, which is a south pole. Pretty cool. All right, so enough about magnets. How can we actually relate electricity and magnetism? Because like this whole unit is about E&M, electricity and magnetism. So magnetic fields are actually produced by electric currents. They're not always, no, always, I'm sorry. And these electric currents can be an actual electrical currents in a wire, or it can be created by electrons moving inside the magnet. Remember, everything is made up of atoms, right? And every atom has electrons. So everything has electrons inside of it, okay? And those electrons moving can actually create a magnetic field. All right, so now here's where we start getting into our right-hand rules. This is the first right-hand rule, and it's the straight wire right-hand rule. As we do our right-hand rules, I'm going to like do my best to turn so that the little image of me matches what's happening in the picture. But if it doesn't, trust the picture, don't trust me. Okay, so your right-hand rule is always used with your right hand. Duh, sorry, lefties, sorry, Georgie. Don't worry, I struggle too. So you're always going to have to use your right hand. So with a straight wire, and this is only for a straight wire, so this is called the first right-hand rule. You can find the direction of a magnetic field due to a current. So what you do is you use your thumb to point in the direction that the current is traveling along the wire. So in this picture, I see that it is moving from right to left. Or right to left? I'm sorry, I'm struggling. So what I'm going to do is I'm going to turn around a little bit and I'm going to take my hand, all right, and I'm going to point my thumb in the direction of the wire. All right, and I want you to do this with me, okay? So take your thumb, point it in the direction. And then what your fingers do, right, if you kind of make your hand, you curl it like you're grabbing the wire. And as you grab your wire, your fingers point around kind of in a circle, right? And this is the direction that your magnetic field is. So a little weird, I'm sorry, I don't know if this is perfect, but let's look at just this picture, right? So we've got a thumb pointing from the right to the left, right, along the direction of the wire. And we see these fingers kind of curling around and like grabbing the wire. So the direction that your fingers curl from your knuckles towards the tips of your fingers is the direction of that magnetic field. All right, it is circular in direction and it's going up into the page, down, and out of the page. Okay? Please take a second, make sure you write down this right-hand rule and make sure that you, I would say, explain it, and also make sure that you note that this is for straight wires, okay? A straight wire. All right, so these are two different symbols that I also need you to jot down, okay? We use this little circle and then a circle filled in to denote that something is coming out of the page, okay? And then we use a circle with an X in it to mark that something is going into the page. Because all of this is very 3D, but we're obviously solving problems and doing notes in a two-dimensional space, we need to be able to show things as moving into a page of paper or out of a page of paper. Sorry, I need to jot that down for myself because I sometimes forget. Crazy, right? I remember when I first learned this, my physics teacher, right, like if you have a piece of paper and you go into it, right, it like makes that hole, and that's where the symbol kind of comes from. Whereas if you pull out of the page, right, the paper kind of comes out with it and looks a little bit more like an X, and that's where the X comes from. Take it or leave it, maybe just memorize it, whatever works best for you. All right, so what exactly is an electromagnet? So a solenoid is a long coil of wire, and an electromagnet is created when we take a current and run it through a solenoid, okay? It'll act just like a bar magnet, but it's not a bar, right? It's a piece of wire that's been curled up and coiled around. So here are two examples of solenoids. Right here, we've got one without a nail through it, and then this one has that nail running through it. Kind of cool. So take a second. I want you to notice, what do you like, make some commentary about this. Like, what do you see happening in both of these pictures? Jot it down, and when you're ready, let's move on. Okay, so now we're going to talk about our second right-hand rule, and this is the right-hand rule with a solenoid. So what you need to do is, with a solenoid, the first thing you'll need to think about is the direction that your current is flowing. Remember, our conventional current comes out of the positive terminal and back into the negative terminal, okay? So on this solenoid, we are saying that the positive terminal is right here, right? There's a wire, and that's where the charge is entering the solenoid. So what you will do with your solenoid is you will grab it with your fingers, okay? And your fingers need to go in the direction of the current. So if I were to take the solenoid and grab it, what I would do is, I think this will be right for you guys. I'm taking my hand and kind of wrapping it from the front of me back, because I look at this wire and I see it kind of comes out towards me and then away from me, towards me, away from me, towards me, away from me. Okay. Another thing that you can kind of think about is that, never mind, I'm sorry. So when you wrap your fingers around in the direction of the current, your thumb will point to the North Pole, okay? So because a solenoid acts like a bar magnet, it has a North Pole and a South Pole. And as you wrap your fingers around it, right, you get a North Pole. In this magnet, right, and then this picture actually is like a hand around it, right? So this wire comes forward and then back. So what our fingers are doing is they're starting at the front and wrapping around towards the back. And your thumb, sticking straight out, will point in the direction of the North Pole. Okay? Cool. So a little bit different than our straight wire rule. In this version of our right-hand rule, our fingers represent the direction of current and our thumb represents the magnetic field. In our first right-hand rule with a straight wire, they were flipped. Our thumb was current and our fingers showed us the magnetic field, okay? Please make sure you write both of them down and make sure you notice the differences between the two of them, okay? Highlight, underline, whatever you gotta do so you can tell the difference. All right, so we are going to do a little practice. You have these examples in your notes, so feel free to follow along in that note section or in your own notebook. Okay, so we're going to draw arrows showing the direction of the magnetic field. Okay, so this first example, is this a solenoid or a straight wire? Well, it's a solenoid, right? I've got wire wrapped around. So what we need to do is we need to say, okay, I see this little arrow which is showing me the direction of current. So current is starting forward and wrapping back. So my right hand needs to start forward and kind of wrap around away from me. And that makes my thumb point to the left. Again, my apologies if you're not able to see it via me. Definitely try it for yourself and make sure that you are getting the same thing. So this is our magnetic field. We use B for magnetic field. It is a vector, so it gets the little hat on it, okay? Let's look at this next one. This is now a straight wire or a solenoid. It's a straight wire. So because it's a straight wire, we're gonna go back and use our first right-hand rule. Okay, so I've got my thumb pointing in the direction of the current, and I'm gonna take my hand and wrap it around, right? If I were to grab that wire, right? Pretend you're just take your thumb to match it and grab the wire. My current would go into the page, and then at the bottom, right, because it keeps going in a circle, it would come out of the page. So I'm just gonna give that some X's and some O's. And I should probably fill these in. If you wanna just give it an O because you're typing, like that's cool. I will know what you mean. And we're just gonna do that all along here, okay? God, these are really bad, but you know what, it's fine. It's fine, okay? We're doing the best we can, virtual instruction. Okay, so now this next one, is it a solenoid or a straight line wire? It's a solenoid, look at all those loops. Okay, the first thing we need to do is decide what the direction of current is flowing. I see a positive battery terminal right here. Remember, if it doesn't say positive and negative, the positive is the longer one. So my current is going out here and it's starting this way. And I see that this solenoid is wrapping away and then towards me. So what I need to do is take my hands and it's going away from me and then towards me. Away and then towards, okay? Try it for yourself. What direction does your thumb point? My thumb points out this way. So this is our B. Okay? And I want to be clear, technically, right? We've got all these magnetic field lines that are going out this way and in this way. But you know, I want to teach you this, but for you to just draw the one is cool, okay? We're just trying to do our best here, right? Same thing with this one, right? There's a bunch of field lines that are going out this end and out towards this one, just like in this picture, okay? But for you to just show me the direction of north is plenty, okay? This is our last example. So I've got a straight line wire coming straight out of our page. So I'm going to pretend it's coming straight out of the page and I'm going to wrap my fingers around. My fingers are going counterclockwise. I'm not sure if you can really tell with my image, but here we go. So it looks like this. And I'm just going to say B, okay? It's going counterclockwise. Just draw one, and that's plenty, okay? If you have any questions, please make sure that you write them down, jot them down, and ask me during office hours. I know this is a lot. All right, so right now I would recommend you complete the section of the assessment that's titled Electromagnets Assessment. And when you're done, I would pause the video, I'd get it done, and then when you're ready, let's move on and learn a little bit more, okay? Here are a couple extra practice problems if you want to try them. Pause, and then you can check your answers right now. Here are the answers to these. I'm kind of combining a couple lessons and shortening them a bit, so if I forgot to get rid of the X ticket, sorry. All right, so now we're going to talk about magnetic force, okay? It's a force. I usually give it a little M, just so I know it's a magnetic force. Like any other force, the units are newtons, okay? So a magnetic force is experienced by a charge when it's in a magnetic field, when the charge is moving and the velocity is perpendicular to the magnetic field. Please write that down. So a charge will experience a magnetic force in a magnetic field when it's moving, but it's perpendicular to the direction of the magnetic field. Okay? Cool. So moving on. Here is my favorite right-hand rule. Okay? So because all of these are vector quantities, without getting too deep into like crazy E&M stuff, okay? We can use our right-hand rule to determine magnetic force, because magnetic force is the product of two different vectors. It's the product of the velocity or current of a charge crossed with the magnetic field that it's in, okay? So using our right hand, okay, you can use your fingers to say, hey, here's the current, here's the velocity. If you look at this picture, so it shows like this weird like thing going on, and the deal is all of your fingers need to be at right angles, right? So you've got your pointer finger out, and this one will represent the velocity or the current that a charge is in. Your middle finger pointing straight out now, making like this weird L, represents the magnetic field that a charge is in. And then the direction that your thumb points, pointing straight up, is the magnetic force experienced by the charge. This is fine. I'm going to be honest with you guys, you're going to be doing right-hand rule problems and you're going to look like an idiot trying to twist your hand around to make it work. If you are struggling, because I personally like this is not comfortable and I like get my hands all mixed up. I always say, okay, my fingers are going to point in the direction of V and then curve toward the direction of B, right? So, okay, if V is straight out towards you and then B is this way, I'm going to curve my fingers and it gives me the direction of my force. V cross B, and that just is easier for me. Or, V cross B, right? You kind of flip your hand around to make sure that you can turn it however you need to. And then your thumb just pointing straight out will give you the direction of the force, okay? Again, always use your right hand. Take a second and write down what each of your fingers represent, okay? Thumb pointing straight out is your magnetic force. Either your pointer finger or all your fingers point in the direction of the velocity or the current, and then your middle finger or your fingers curve in the direction of your magnetic field. Sounds crazy, I know, but let's try it. It's honestly kind of fun. All right, so we have this practice problem. We want to determine the direction of the force on this positive charge when entering a uniform B field in the direction indicated. Okay, so I see that B is straight up and the velocity is to the, the right? Okay, so let me turn my body here. So my velocity is to the right. So I've got my fingers going to the right, but then my magnetic field is up. So I need to curve my fingers up. When you do that, what direction does your thumb point? Mine would point straight out of the page, okay? If you are doing the other version of the right-hand rule, it's the same thing, right? You gotta like take your hand. Okay, so my first finger is the velocity. My middle finger needs to point in the direction of the magnetic field. What direction does your thumb point? Again, right out of the page. Use whichever like hand thing you like better. This is just like so awkward and I feel like such a loser trying to like twist my arm around to make that happen, but you do you. Either way, we should get that the force is straight out of the page. And so we would indicate that by saying Fm equals, and we would just draw the little O filled in, or no, I'm sorry. We would draw the little Fm equals circle with that X through it for out of the page. Okay, cool. All right, so we have a couple of equations for you to write down. The first one is F equals B times I times L. So our magnetic force equals the magnetic field, which we measure in Tesla, capital T, write that down, times I, the current in amps, times L, the length of the wire in meters. So this is specifically if we've got a current running through a wire, we can calculate the magnetic force. Okay? Take a second, pause me, write this down. I recommend you write it down on your formula sheet so you have all of your formulas in one place. Just saying. All right, so we've got one example. I believe just one on this. A wire is 0.5 meters long and carrying a current of 8 amps to the right through a 0.4 Tesla magnetic field pointing upward. We want to know how strong is the force that acts on the wire, and we want to know its direction. So I was given the length, 0.50 meters. We were given a current, I, of 8.0 amps. And we were given a magnetic field, B, of 0.40 Tesla. Okay, so we've got a B, we've got an I, we've got an L. Pretty straightforward. Our force is going to equal B times I times L. So we get that it will equal 0.5, oops, times 8. Wow, this is so bad. I'm sorry, you guys. Times 0.4. Hopefully your handwriting is better than mine. We'll take our handy dandy calculators, right? 0.5 times 8 times 0.4. I got 1.6. Double check me. I hope you get 1.6 too. Our force of the magnetic field is 1.6, but we're not done. We have to have a unit. What unit is that? Newtons. All forces are measured in newtons. So we answered the first question, but we need to make sure we answer the second question as well. The second question asks us about the direction of the force. So to find the direction, we're going to use our handy dandy right hand rule. So I'm going to kind of flip around here. So my current is going to the right. No, this is right now. Yeah, because I'm flipping. Okay, so my current is going to the right. And then the magnetic field is pointing straight up. So if I point straight up, that puts my force at going, sorry. So my my current is to the right, so I've got my fingers going to the right, and then my magnetic field is up, so I curve my fingers up. My thumb points into the page. Let's see. Oh, out of the page. Sorry, I'm trying to do all this like flipped for you guys. Oh, gosh. Okay, let's try that one more time. Okay, so we got our answer at 1.6 newtons. That was good. To the right, up, out of the page. Try it for yourself. If you're struggling to get out of the page, please come to office hours. I know the right-hand rule is a little wonky, but I believe in you, okay? You got this. All right. Next thing, magnetic force will also equal QV times B. Technically, these are vectors, right? So it's QV cross B, but we're not going to worry about that. We're just going to say times, okay? So F, and again, give it a little M for yourself so you know which force it is. Force of the magnetic force will equal the charge times its velocity times the magnetic field that it's in, okay? That's how we get our final value for magnetic force. Jot it down, write it on your formula sheet, make sure you include units for everything so you know what you're talking about. Write this down too, okay? The charge of a proton or an electron is 1.6 times 10 to the negative 19 coulombs, okay? If it's a proton, it's positive. If it's an electron, it's negative. Crazy, right? The right-hand rule is only used for positive charges, okay? Write that down too. Right-hand rule is only used for positive charges. So if you are given a negative charge, you use your right-hand rule. And for example, if the force says it's going up, well, but my charge is negative, so I just need to flip it at the very end and say it's negative, okay? If you've got a negative Q, just take the opposite direction of what your right-hand rule will tell you, all right? Easy peasy. All right, so we've got a particle with a charge of negative 5.6 coulombs that's at a right angle to a 23 Tesla magnetic field into the page. The particle is traveling with a velocity of 7 meters to the left. How strong is the force that acts on the particle? Okay, so let's get our pen. This right here is my Q. This right here is a B value, right? It's a magnetic field. And then this right here is my velocity, okay? So to find my force, we're gonna take Q V times B. So we're gonna take my magnetic force equals this 5.6 times 7 times 23. And then let's see what we get. Oops. 5.6 times 7 times 23. I got 901.6. And that's 901.6 newtons. Make sure you give it a unit. All right, so now our magnetic field is into the page, okay? So, and my velocity is to the left. Pretty sure I'm doing this right for you guys. I'm getting that the force is down, but if it's down and this is a negative charge, that really means the force is acting up, right? We need to flip it at the end, okay? All right, I'm gonna move to the next slide. Let's see if we were correct. All right. So we had to flip the direction of the force at the end. We've got our givens, cool. 901.6 up because it's a negative charge. Oh, I forgot to say that this was a negative. So a negative times all of this would give this a negative as well. My fault. Hopefully that made sense to you. All right, so the last thing you need to do is complete the section of the assessment that's titled Magnetic Force. That's it for our lesson. I know the right-hand rule is a little wonky, but I believe in you. I know you guys can do it. This assessment does have a grade associated with it. Do your best. Come to office hours. I hope you're all doing well. I love you tons, and I hope to see you soon. Love you. Bye.